From distant space, the Earth appears like a color compendium. A touch of brown where the crust is bare, green shades like pastel strokes where forest covers the land, and there is white from the clouds that sail in the atmosphere. Yet, in totality, it looks blue, a blue marble, because this mysterious third planet from the Sun is known to contain a fluid, water, the lifeline of the Earth. Most of the Earth is covered with water. Water is in the atmosphere, in the core of the Earth, and it covers the Earth's surface in the forms of lakes, rivers, and oceans. We feel curious. Where does the water come from? How did it form? And is there enough stock of the liquid that apparently is so abundant? The development of our universe has been successfully described in mathematical terms from 10 to the power of minus 35 seconds after its creation, which supposedly happened some 15 billion years ago. In the beginning, all of the matter and energy of space was contained at one point. A tremendous explosion started the expansion of the universe. This explosion is known as the Big Bang. Immediately after the Big Bang, the universe was tremendously hot. It began to expand and cool. After the universe had cooled to about 3000 billion Kelvin, composite particles such as protons and neutrons became the common state of matter. Current models of the Big Bang predict that hydrogen should have been produced 3 times more abundantly than helium. So, how are the heavier elements, such as oxygen, formed? They are synthesized during the evolution of stars. When atoms for exothermic fusion become no longer available in stars, helium begins fusing, and one of the byproducts of that process is oxygen. Depending on the mass of the star, all the heavy elements up to iron can be created in succeeding fusion reactions or nucleosynthesis. We wonder how the oxygen that formed in the core of the stars ever got incorporated into our planet. Well, one rather dramatic way occurs at the end of a very massive star's life. Once iron is formed in the core of these stars, there are no further nuclear reactions. Without the output of energy to balance the star's inward gravity, the star collapses upon itself, leading to its destruction in a supernova explosion. A supernova remnant formed from the exploded star expands outward, and eventually all the elements within it are spread throughout the galaxy and mix into the region between the stars. Over time, denser regions of the interstellar medium form into giant interstellar clouds of gas and dust. These clouds are stellar nurseries in which numerous stars will be born. Around each star, residual gas and dust slowly congregates and forms into planets. Thus, the planets and we are in fact all made out of star stuff. Now, given the creation of hydrogen in the Big Bang and oxygen in nucleosynthesis in stars, and the fact that these elements are highly reactive chemically, water should therefore be fairly common in the universe. However, only at certain temperatures and pressure, like those we find on Earth, would we expect to find liquid water. Left to itself in space, Earth's surface water would create a sphere 2,400 kilometers in diameter, big but smaller than numerous icy bodies in the solar system. The origin of water on Earth is by no means certain, and numerous mechanisms have been advocated. Proponents of condensation theory believe that water accumulated on the Earth's surface through a condensation of water vapor in the atmosphere. This theory has fallen into disfavor as no Earth atmosphere could hold all water of the planet in suspension. Hydrosphere is believed to be outgassed and condensed from the interior of the Earth. But in that case, there should be 20 to 40 times more water on Earth. The planetary picture that is emerging is that Earth was formed with very little water or no water at all. The hydration of Earth came from comets and some hydrous asteroids. Water is thought to have been first delivered here over 4 billion years ago, involving an intense bombardment of the inner solar system. One such attack is known as the Lunar Cataclysm, a period of celestial assault when the moon became most heavily pockmarked. The Earth received 13 to 500 times more hits, and having a greater critical mass was also able to hold much of the water, ice, whereas the moon lost most of its frozen water to the emptiness of space. How long the water on Earth will last? The water we drank this morning might have been the same water a dinosaur drank millions of years ago, or it may have been the same water that supported Columbus's ships on the sea. We have reasons to believe that there is more or less the same amount of water on Earth today as there's always been. On Earth, the water keeps moving around in an endless cycle called the water cycle. Water itself is the only substance that exists in liquid, gas, and solid form, the keys to the water cycle. Spacecraft have at least partially explored all the planets around the Sun except Pluto. However, an analysis of the chemistry of a sample of the surface or of the atmosphere of each of the planets has been quite limited. Detecting water in the universe up to now has been done almost entirely remotely. Till date, we can give only a partial list of evidence of the existence of water in the universe. Frozen water makes up 75 to 80% of any comet's mass. Comets are chunks of dust and frozen gases, including water, that rotate in highly oblong orbits around the Sun. They are sometimes referred to as dirty snowballs, although they are many kilometers in size. As they near the Sun, the sunlight melts some of the comet's material, which results in a long tail. Some astronomers have raised the possibility that comets have fed the oceans with water through numerous collisions with the Earth over the eons. For centuries, astronomers have known that the airless, sun-baked moon is dry. But the discovery of craters with permanently shadowed floors near the lunar poles raised an exciting possibility. Perhaps these dark hideaways contain water ice that could be mined by future astronauts. But now scientists probing deep into the polar surface with radar have concluded that lunar ice, if present, will be more difficult to extract than some have proposed. Probably it's worthwhile to send a probe into the shadowed regions to measure not just water, but other volatile materials. Earlier, scientists believed that there is no evidence of the presence of water on Mercury. Its outgassing must have been quite complete, with every molecule of water decomposed by ultraviolet solar radiation and swept away by solar wind. The planet lacks atmosphere and resembles our moon, both in size and its heavily cratered surface. But planetary scientists have now become increasingly convinced that the planet's polar regions are dotted with thick, permanent slabs of water ice. The existence of highly reflective poles revealed the possibility that ice could be the source of the reflections. The existence of ice on the planet, where daytime temperatures reach 825 Kelvin, is actually very possible due to the fact that Mercury spins on an axis that is almost perpendicular to the plane of its orbit, and therefore it does not have true seasons. Because the Sun is kept almost directly over Mercury's equator, the poles are always at the edge of the sunlit side of the planet. Thus, flat areas on the poles receive so little solar energy and long shadows that keep polar crater floors in virtual darkness. These shadowed crater floors have maintained temperatures as cold as minus 213 degrees Celsius, and this is well below the temperatures needed to retain water ice for billions of years. Venus, although a twin planet of the Earth in size, has surprisingly little water in its carbon dioxide atmosphere. However, no water exists on its basaltic surface, which, with a temperature of 650 Kelvin and clouds of sulfuric acid overhead, resembles a classical vision of hell. Measurements made by the Pioneer Venus orbiter during the latter stages of its 14-year exploration of Venus suggest that the planet very well could have been relatively wet in the distant past. This spacecraft found that the ratio of deuterium to plain hydrogen is some 150 times greater than on Earth. This excess is likely due to the escape of the lighter isotope over the ages. If this is the case, then Venus may have had 150 times as much water as it has today. Even the earliest spacecraft photographs of the famous red planet Mercury show long, jagged structures that appear to be old rivers and canyons. Photographs taken recently by the Pathfinder lander show stacked boulders that were probably deposited by raging floods. The atmospheric pressure on Mars is now 100 times less than ours, and therefore water cannot exist as a liquid there anymore. It is possible that much of the water in Mars exists as subsurface ice. There are polar ice caps on Mars that get larger during the Martian winter and smaller in the summer. The ice caps are largely composed of frozen carbon dioxide, but small amounts of water ice have also been detected. The bottom line is, like any desert, there once was water. Scientists now believe that there is evidence of once flowing water on the surface of Mars. And if so, a manned mission would be interesting. If we don't find life, we might find the prebiotic chemistry that went into life on Earth. That's more important because we know what life is, but we don't know about the precursor chemistry that went through. Although Jupiter is about 70% hydrogen, it also contains huge quantities of oxygen, nitrogen, carbon, silicon, aluminium, and other heavy elements. But the amount of water in Jupiter is yet hard to estimate. Jupiter's moon Io, like Venus, is a medieval vision of hell. It lies in the deadly sphere of the Jupiter's radiation, where 1 meter of lead would be a barely acceptable shield for humans. However, the surface of another moon, Europa, appears cracked with many fissures, as if it is made of ice that freezes and then thaws repeatedly. There may actually be a liquid ocean under the ice. Ganymede, another of the 4 moons, has a similar looking surface but to a lesser degree. Ganymede, the 3rd satellite of Jupiter, is the largest moon in the solar system. It is known to exhibit faulting, and the faulting material is ice. Scientists suspect huge undersea oceans may lie beneath the surface of the ice. Saturn, the most beautiful celestial body known, owes its splendor to a spectacular celestial display of frozen water. Its eminent rings are poor reflectors of sunlight at certain near-infrared wavelengths, which indicate water ice. Uranus and Neptune are similar in size and supposedly in constitution. Compositionally speaking, they can be considered as giant collections of comets. The three-layer model of these planets features a gaseous atmosphere, a liquid ocean, and a rocky core. The two-layer model, preferred after Voyager missions, predicts a superdense atmosphere containing up to 50% water and a rocky core. Undoubtedly, the interior of these planets is one of the most intriguing in the solar system. Some theories suggest, for example, a superheated ocean some 8,000 kilometers deep. Pluto's surface is far too cold for liquid water, but its interior is probably warm and maintained that way by the slow decay of naturally occurring elements such as uranium, potassium-40, and thorium. Enough heat is released so that a water ocean may exist between the rocky core of Pluto and its thick outer layer of ice. Pluto's ocean is also likely to contain biogenic elements in a solution, especially if it is in contact with an organic rich layer. Behind molecular hydrogen, water is the second most abundant molecule in the universe. Water is ubiquitous. Water indeed exists everywhere in our solar system and beyond. It appears, though, that only on Earth can the water be exploited in all its three physical states, and hence for life's sustenance.